Okay, welcome to today's lecture on electrostatic force. Another name for electrostatic force is Coulomb's law. This is a force that we have not talked about yet this year because it's a very specifically electricity-based topic, and we hadn't gotten to electricity yet. So some of the variables that are going to matter we hadn't talked about yet. I was waiting until we started the electricity unit to talk about them. In class, what you'll see me do is a demonstration where I hang two balloons from the same point, and you'll notice that the balloons are separated like this. That's kind of weird. Usually things hang straight down, but the balloons then in this demonstration will be separated. And one of the questions is, well, why are those balloons separated? Based on what we've talked about so far and some of the examples we've seen, you might come to the conclusion that maybe each of these balloons has some sort of electric charge on it. Maybe it's the same type of charge, like either both balloons are either positive or negative, and therefore they are repelling each other. And that would be the correct answer. If I give both balloons the same type of charge, either both positive or both negative, then even though they're hanging from the same place, they will hang like this. They will actually repel each other, and both strings, both tensions, will be at an angle. If this is the case, then a free body diagram for one of the balloons would look like this. Let's take the left-hand one. Okay, here's my dot. It says balloon. I know that there's a force of gravity on the balloon. I know that there's tension from that string. Oh, I need an axis. Now, if these were the only two forces on the balloon, I would expect the balloon to be accelerating to the right. But in this case, the balloons are just kind of hanging there. They're not accelerating at all. I need something to balance out this force of tension, and that force would be the electrostatic force on the balloon, the force due to another charged particle. We symbolize that with Fe, the electrostatic force. Okay? And since we're saying in this situation that both balloons are positive, that means they repel each other. That means the right-hand balloon puts a force on the left-hand balloon to go away from it. Okay, that would mean to the left. So there's a real basic free body diagram for this balloon. Now, those balloons are not touching each other, okay, but they are exerting a force on each other, an electrostatic force. That's weird. Usually when we have forces, it's because that they are touching each other. So this electrostatic force, it's a little strange. It's kind of like gravity. You don't need two objects to be touching to have a force of gravity between them. The electrostatic force is similar. All the other forces that we talk about, the normal force, friction, applied force, tension, spring force, they all need two objects to be directly touching in order to be exerted. The electrostatic force, and the force of gravity for that matter, is just a little bit different. So this electrostatic force, let's think about what sort of factors might play into how big this force is. You might guess how much charge is on each balloon plays a role, and you'd be absolutely right. More charge usually means more force. Another thing that you might guess matters is how far apart the balloons are. If they're farther apart, usually that seems to mean a weaker relationship or a weaker link between the two of them. And it turns out that is correct as well. Well, thankfully, we know the exact relationship, the exact equation that describes the electrostatic force between two particles, two electrically charged point objects. And we're going to talk about what point objects means a little bit later, but for right now, we're going to just take a look at the equation. We're going to go on the reference tables to page 4. We're going to go to the very top of page 4. It's the electricity page, and this very first equation is where we're going to start off. Fe equals K Q1 Q2 over R squared. We see that Fe is the electrostatic force. K is something called the electrostatic constant. Q, it's a lowercase q, notice it's not internal energy. Lowercase q stands for charge, so Q1 and Q2 are charge 1 and charge 2. And R is the distance between the centers of the charges. So let's just write that down. Fe is electrostatic force. Since it's a force, it would be measured in newtons. Now K is a little tricky. K is the electrostatic constant. Don't get this confused with spring constant, which unfortunately has the same variable. It's also a K. Spring constants have to do with springs. A spring constant is different for every single spring. The electrostatic constant, however, is a constant that is universal. It applies wherever. It's not dependent on the situation. Okay? If you know that you're going to be using this equation, K, the electrostatic constant is always going to be the same. Totally different from the spring constant. It's listed on the front, and just as a quick rundown, we've discussed universal gravitational constant. We've discussed acceleration due to gravity. We haven't talked about speed of light or sound, but we've used the mass of the Earth and the Moon. We've used the mean radius of the Earth and the Moon, and the mean distance, Earth to Moon and Earth to Sun, in our gravitation unit. We've talked about elementary charges in coulombs and how they're related to each other. There's our electrostatic constant, K, 8.99 times 10 to the 9th, newtons times meter squared over coulomb squared. And then finally, to wrap things up, we're going to be talking about these 6 down here at some point in the next few months, okay? Occasionally in this unit, you have to know rest mass of proton, electron, or neutron, but that'll come up more towards the end of the year. In any case, the electrostatic constant is a constant that makes this equation work. 8.99 times 10 to the 9th, newtons times meters squared over coulombs squared. And yes, you do have to include the equations, but they're listed right on the reference tables for you. Q1 and Q2 are charges, electric charges specifically, and 2 things about them. They must be written in coulombs. K is a constant that has units of coulombs. Q1 and Q2 also have to be written in coulombs. So if you're given charges and it's just a number of elementary charges, you need to convert. Also, when you're using this equation, you are going to use only the magnitude of each charge. Now what that means, magnitude, means size. All I'm telling you is that you're not going to put the sign, the positive or negative, in there. You're just going to leave it off. Even if a charge is negative, you're not going to put that into the equation because it'll just confuse you. And then finally, R is the distance between the centers of charge. Which actually sounds kind of familiar. Matter of fact, this whole equation should look kind of familiar because it has the same format. It's not the same thing, but it has the same format as this equation, the gravitation equation. Remember, that was Fg equals G m1 m2 over r squared. This is Fe equals K, a constant, Q1 and Q2, 2 charges in place of 2 masses, over, again, r squared. So that's interesting. We won't talk too much about that now, but we will come back to that later on. The fact that it looks similar to the gravitation equation has been important in the last 100 or so years of physics. The reason that it's been important is because it inspired some people to look for links between gravity and electricity, 2 seemingly completely unrelated phenomena. And in the study of physics over the past 100 years, this has allowed us to actually make some interesting discoveries about the nature of force in our universe. That's all I'm going to say about it for now, but I just want to point out it is interesting that those 2 equations look so similar. Anyways, going back to Coulomb's law, that's another name for this. You can either call it the electrostatic force law or Coulomb's law. This law works best in a couple of situations. It works best for, like we set up here, what we call point objects, or point charges. These are things like electrons, protons, or any other physically small, as in small in size, small in volume, space, charges. It works best for things that are very small. Okay? Not small in magnitude necessarily, but small in size, because you can pretend that the charge is concentrated at one point. For that same reason, it also works very well for spherical objects, objects that are, well, spheres. The reason it works good for spherical objects is because we can imagine that we can take that sphere and just condense it down into a point. Okay. There are other situations where you have objects that are not point objects or are not spheres. We're not going to worry too much about the electrostatic force from those things. If you take like a college level electricity and magnetism class, then you will spend some time talking about that, but that's above the scope of what we're going to do. Now, I said that you're not going to put the sign in the equation. You're not going to put negative signs or positive signs in the equation. You might be asking, well, then how am I going to know if this is if the force is attractive or repulsive? Remember, attractive brings things together, repulsive pushes things apart. Well, that's not going to be too hard. You're going to know based on whether the charges are the same or different. If the charged objects that you put in for Q1 and Q2 are of similar signs, remember, you're not going to put the signs in, but you know what the signs are. If the charged objects are of similar signs, then the force will be repulsive. The objects will repel, just like the two balloons. If they are of different signs, then the force will be attractive. So that's just something you should note at the beginning of each problem. Is the force going to be attractive or repulsive? Now, in class, I'll talk a little bit more about this, a little extra credit assignment, determining the product of the charge on the balloons. Okay? There's some math you can do along with this free body diagram to determine an equation for calculating what the product of these charges are, the charge on each balloon, given the situation and a few measurements. We're going to skip that for right now, though. We're just going to go to the back and look at some examples. Before we get to the examples, let's just make sure that we have everything on here. Okay? But before we get to the examples, we're going to take a look at these two graphs. We're going to sketch graphs of how the electrostatic force is related to both the charge and the distance between charges. Remember, our equation is Fe equals K Q1 Q2 over R squared. How is the electrostatic force related to the charge? Well, if the charge is doubled based on where it is, here's Q1. If we double that charge, that seems like it's going to double the electrostatic force as well. If we were to triple the charge, that'll triple the force. Quadruple the charge, quadruple the force, and so on and so forth. That means we're going to end up with an equation like this, a linear equation. So we can say that the electrostatic force is proportional to charge. Whatever factor we change one of the charges by, that will change the electrostatic force by the same factor. The distance is a little bit more of a complicated relationship. We see that it's in the bottom, the distance between charges, so we know that if we increase the distance between charges, that's going to decrease the electrostatic force. And there's a squared attached to it. Now, we've seen this type of relationship before. The graph ends up looking like this. And it is known as an inverse square relationship. The other time we saw this is when we looked at the gravitation equation. That was also an inverse square relationship. Okay? Those are two graph shapes that you have to know. You have to understand those relationships. Let's get to some examples where we actually calculate. In a hydrogen atom, most basic atom you can have, the orbiting electron is about 5 times 10 to the 11th meters from the proton in the nucleus. What is the electrostatic force between the electron and the proton? Well, my equation is Fe equals K Q1 Q2 over R squared. I should just be able to plug everything in. I know everything that I'm going to need to plug in. Or I can look it up. K is the electrostatic constant. Remember, 8.99 times 10 to the 9th newtons times meters squared over coulombs squared. Now, Q1 and Q2 are the sizes of each charge. We have an electron and a proton. It doesn't tell us the charges, but we know that an electron and a proton have the same charge, and it's the same charge as one elementary charge. That's what an elementary charge is. It's the amount of charge that either an electron or a proton has. Electron has a negative elementary charge, proton has a positive elementary charge. remember that these charges need to be in coulombs. So we go to the reference tables again. One elementary charge is 1.6 times 10 to the negative 19th coulombs. I'm not going to put one of them as negative because remember we leave the signs out of this equation. However, we do know that since it's an electron and a proton, they have opposite signs, they have opposite charges, therefore these two particles will be attracted to one another. The distance between the charges is 5 times 10 to the negative 11th meters. And don't forget, you have to square that. Now, this is a good time to practice typing scientific notation into your calculator. If you've got a calculator that looks something like this, 8.99, hit the EE button, times 10 to the 9th, times 1.6 EE negative 19, times 1.6 EE negative 19. I get 2.3 something times 10 to the negative 28th. And then what I like to do is I'm going to do divide, open up a parentheses, 5 EE negative 11. I'm going to square that. I'm going to end the parentheses and then hit equals. The other way to do that is to divide by 5 times 10 to the negative 11th once, hit enter, hit equals, get a result, and then do the same thing again. Divide by 5 times 10 to the negative 11th again. You should get the same answer. This answer is, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Fe equals 9.2 times 10 to the negative 8th newtons. And since it's a negative charge and a positive charge, we know that it must be attractive. The electron and the proton are attracted to each other. Is this one of the forces that holds an atom together? I don't know. Let's see. What else could hold the atom together? Perhaps the force of gravity. Okay? They both have mass. They could be gravitationally attracted to one another. Let's try it. Fg equals G m1 m2 over r squared. Remember that G, the universal gravitational constant, big G, 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Notice right now that that constant is tiny compared to the electrostatic constant. Electrostatic constant is huge. It's like 899 million or maybe 8 billion or close to 9 billion. This is tiny. It's far less than 1. So that's kind of interesting. Mass of proton and mass of electron are listed right here. Proton's mass is 1.67 times 10 to the negative 27th kilograms. Electron is right above it, 9.11 times 10 to the negative 31st kilograms. And the distance between the centers is the same, 5 times 10 to the negative 11th meters. And we come up with an answer of 4.06 times 10 to the negative... Oh, did I do something wrong? I think I did. I had the wrong exponent on there. There we go. 4.06 times 10 to the negative 47th newtons. Now this is an attractive force, because gravity is always attractive. But look at how much smaller this force is than this one. Matter of fact, if I were to do the size of the electrostatic force, which is pretty small, based on our standards, divided by the force of gravity for an electron and a proton, I get something that is almost 10 to the of difference, a factor difference of almost 10 to the 40th. Here's what that means. For an atom, for an electron and a proton that are attracted towards each other in an atom, Fe is nearly 10 to the 40th. That means a 1 followed by like 40 zeros times stronger than Fg. The force of gravity basically does nothing to hold the atom together. Okay? Gravity is only strong. It's only, not useful, but it's only relevant when you have huge masses. These masses obviously are very small. The electrostatic force, on the other hand, is relevant even for small objects. It actually gets less relevant for bigger objects because bigger objects tend to be neutral. But the electrostatic force is much bigger on small scales than the force of gravity, typically. So what this means is that the electrostatic force is part of what helps hold these atoms together. Kind of interesting. And we'll talk more at the end of the year about the relative sizes of all these different forces. Two more examples. Two charges are placed in a row as shown below. We have a charge of positive 1e and positive 2e. There's a distance of 8 times 10 to the negative 9th meters between them. What's the electrostatic force between charge 1 and charge 2? We notice that these charges are the same signs, so this must be repulsive. That gets added on at the end, though. Fe equals K Q1 Q2 over R squared. K from the reference tables is 8.99 times 10 to the 9th newtons times meters squared over coulomb squared. Q1 is the charge of object 1 in coulombs. Since it's one elementary charge, that means that, well, since one elementary charge is 1.6 times 10 to the negative 19th joules, that's what we're going to plug in. Excuse me, coulombs, not joules. Two elementary charges, we can do unit conversion. Again, since we know one elementary charge is 1.6 times 10 to the negative 19th coulombs, we simply multiply 2 times 1.6 times 10 to the negative 19th. We get 3.2 times 10 to the negative 19th coulombs. That's what we plug in here. And the distance between them is 8 times 10 to the negative 9th meters. The force of the electrostatic force between them, therefore, we're just going to calculate this real quick. We get 7.192 times 10 to the negative 12th newtons, and that is repulsive. They are repelling each other. If they are not locked in place, they will try to move farther apart. Okay, that's really small, but based on these objects, these are probably pretty small objects. That's fine. That's fine that it's so small, because what usually ends up happening is even though it's really small, that big of a force, or that size force, is enough to cause very large accelerations, because these objects will probably have very small masses. Think about the mass of electron and proton. They're tiny. Now, if charge 2 is moved 3 times as far away, what will the new electrostatic force be? We've done a whole bunch of different methods for figuring this out. I'm going to show you one of the methods. Remember, what we've done in the past is we've pretended that everything in the equation, with the exception of what we're solving for, is equal to 1. Remember doing this? I know it's not actually 1, but let's set K equal to 1, Q1 and Q2 equal to 1, and R equal to 1 as well. 1 times 1 times 1 is 1. 1 squared is 1. 1 over 1 gives us 1. Then what we do is we say, okay, well, we know that the factor of change is the distance. R gets 3 times as big. So K, Q1, and Q2 don't change, but R, what's 3 times as big as 1? That would be 3. Now that's got to get squared. So I have 1 times 1 times 1 is 1. 3 squared is 9. I end up with 1/9. What this tells me is that the new electrostatic force should be 1/9 the size of the old electrostatic force. Well, guess what? I know the old electrostatic force. 7.192 times 10 to the negative 12th newtons times 1/9, which is the same as dividing by 9, gives us 7.99 times 10 to the negative 13th newtons. That's the new electrostatic force, so I just put a little prime there to show that it's new. If you instead went through and you were like, okay, I'm just going to multiply this R by 3 and plug everything in again, you would get the exact same answer. And I encourage you to go and prove that you get the exact same answer doing that method. That's really it for electrostatic force. I'll be back in our next video to talk about what I think is probably the most difficult conceptual thing you will see this year. Not difficult mathematically, but difficult conceptually. That'll be electric fields. Okay? It's really not bad once you get the hang of it, but it is kind of tricky to begin with. It's hard to think about. All right? Electrostatic force, though, pretty straightforward. I will see you for my next video.